So we'll start the third section of the day, and Juan Maldacena will talk about AdS CFT.
Okay, so talking about CFT, so this is between field theories. So in this very important, we'll start with field theory and then take a certain Larsen. So the number of fields will go to infinity. So in CFT, I just want to remind you of a common example of a case where theories simplify when you take the Larsen limit. And so the ON vector symmetry so these are theories that contain fields with n components. So we have some field ni, and I goes from 1 to n. Okay? And the Lagrangian will be symmetric under rotations of ON. So an example of such a theory is, of course, for example, a free theory of n scalar fields. Now, more non-trivial this is a quantum field theory in 2 dimensions of fields that propagate on a sphere. Okay, a sphere in n-dimensional space. Okay. So this is a theory that has a coupling constant, which is basically 1 over the radius of the sphere. Okay. So the smaller the coupling, the bigger the sphere where the fields live. Okay. So this is a certain interacting field theory. In 2 dimensions, this theory is well, let's say it's renormalizable thing, and in the Larsen limit, it's sort of very simple to analyze, and what we are going to see now is how to analyze it in the Larsen limit. It turns out that this theory can also be analyzed exactly, but we will not do that yet. We will not do that today. So the basic trick is to rewrite the Lagrangian as 1 over C naught squared. So we have this n fields, and then we impose this constraint that they propagate on a sphere by adding a Lagrange multiplier. Okay? And now what we do is we integrate out these fields eta, and so we end up with an effective action that will depend only on the field lambda. Okay? So when we do that, we get a term that so we get the determinant for the for this quadratic. So now the field eta appears quadratically in the action. So that's the main simplification, and the we'll get a determinant once we integrate it out. We get a determinant that depends on this field lambda, and in addition, we get the term here, the -1 term that I'm going to rewrite it as. So let's see, we have a minus. Let's see, there is no minus here. Well, let me get the minus sign right. Yeah, there's a minus here, and so there is a minus here. And I will pull out a factor of n, and so we get here G0n times lambda. Okay. Okay, maybe a factor of 2 here. Okay, so now we have this action, and we observe that if we take n to infinity, G square n fixed, then this system becomes a classical equation. System the field lambda, 1 over h bar multiplying the action, and then for to analyze this system, all we have to do is solve for lambda. Okay. So we solve the. So we take ds d lambda equal to 0, and so we'll get a term from the log and a term from that constant, and after rearranging these terms, so from the constant we'll get this one, we'll multiply everything by ng0 squared, and from the determinant we just write it down a little more explicitly, so we'll get something of this form, okay? So the value of the integral will go like the log of some cutoff divided by lambda, okay? So this is an equation that will determine for us what lambda is. So let's first assume, so maybe I should set lambda to a constant. So we write down this equation, and then we set lambda equal to a constant. We look for a solution with a constant lambda, and we see from the equation that the solution with constant lambda has lambda, which is, well, after putting in all the factors, we'll get something proportional to 4 pi n over g naught squared. If we go back to the original action, we see that, well, lambda appears as a mass term for eta. So what we see is that this non-zero expectation value for lambda implies that these eta particles have a small mass. Okay. So initially this model is a model that naively describes massless particles. Okay. So this is a usual nonlinear sigma models in 2 dimensions for fields on a sphere. And sort of due to non-perturbative effects, the field lambda gets some mass. I mean, I'm saying non-perturbative because in terms of what the original coupling was, the dependence goes like 1 over g naught squared. Okay. So here we get a very small mass. Now, notice that here so here we can absorb the cutoff by defining a renormalized coupling. Okay, so we can rewrite this as some scale mu square e to the minus 4 pi n g naught renormalized. Okay, and this equation is also, well, telling us how the runs. So when lambda goes to infinity, g naught goes to 0 logarithmically. Okay, in lambda. So the model is asymptotically free. So it's the same. For example, QCD has that when you go to high energies, the coupling becomes smaller. So here, in these kinds of sigma models, when you go to large energies, the theory becomes weakly coupled. Okay, so what we see here is some nice simplification at large n. We obtain, in a simple way, a non-trivial aspect of this model, like the theory has a mass cap. So it started out in the ultraviolet, it looked like a massless theory, but actually when you analyze it a little better, you find that the theory has a mass cap, the excitations are massive with a mass that looks non-perturbative in this dot coupling. Yes? Yeah. So here the big N limit was used when we was used when we solved for the classical action. So we set lambda to its expectation value. Okay. And then we reinterpreted this expectation value, the mass in the original problem, and that's really a good expectation value. It has small fluctuations because because n is very large. So lambda has a very sort of well-defined web. Okay. Okay. Yeah. Yes. Oh, sorry. The mass is this. You see, in the Lagrangian, m appears as a mass term. So the mass is lambda, and it's this small value. Okay. Okay, so here large n led to simplification, and this theory is rather similar to QCD in the sense that, well, we said it was asymptotically free and has a mass gap, and we could compute it, and the mass gap is visible in the large n approximation. Okay. Now, QCD is a theory where we expect the same properties, so we also maybe would expect that in the large n approximation the theory simplifies, and that we can also see the mass gap and confinement in the large n approximation. Okay, so those are vector theories, and there are similar tricks to solve other vector theories. I mean, you could have other interactions like eta to the fourth, etc. Let's now go to the main topic of this set of lectures, which will be basically large matrix theories. So this will be theories where we'll have n by n matrices. So we'll have some Lagrangian, which will be the trace of some matrix M, and some kinetic term for M, and some, let's say, potential term for the matrix M. Okay. Now this could be in any number of dimensions, and some of the counting that we will do holds in any number of dimensions. So, for example, a theory that looks roughly like this is a gauge theory, where M is the gauge potential. But we could just have a simple theory like a theory of a matrix. Maybe we could have a matrix integral where we don't have a kinetic term, but M is just a matrix, and we're just integrating over the matrix. Okay. So we could consider this theory in 0 dimensions, then we are just integrating over a matrix. We can consider this theory in 1 dimensions, then we have some matrix quantum mechanics. And we can consider many matrices. So for these purposes, we can have many different matrices as long as they are all n by n and have Lagrangians which are of this type. Okay, so we are going to take this matrix to be Hermitian, and when we start writing Feynman diagrams, we'll compute the quadratic term here in the action, and it's convenient in order to keep track of the indices to think of the propagator in terms of 2 lines. The 2 lines will denote the 2 indices of the matrix, of this Hermitian matrix. Okay, so we think of Mij as a Hermitian matrix, and this will be the index I, and this will be the index J. Okay. And then, if we consider here some interaction. So far we've considered the quadratic terms in the action, and now we can consider some term like m cubed. Then the indices here are contracted in such a way that in terms of this double line notation, what we have is the following thing. So we have 3 sort of ribbons that join, so each ribbon is each matrix, and then the indices are constructed in such a way that the arrows, the orientation of the arrows here is preserved. Okay. So as an exercise, you can check that this is indeed the case. And well, the same is true for other vertices, like let's say a quartic vertex. Again, has the same kind of feature. So all the orientation here of the arrows is always preserved. Okay, so. Now this theory will have some coupling constant, let's say 1 over chi squared. So each time we have a propagator, we'll have a factor of chi squared. And each time we have a vertex, we have a factor of 1 over chi squared. Okay? No matter, well, how many lines come into this vertex. Now, suppose we have some correction, for example, to the propagator. So that will be a diagram that will be of this form. This diagram comes from joining 2 of these 3-point couplings. So have all the arrows oriented the way we see here. And so here we'll have, so relative to this diagram, so this diagram went like chi squared, we said, and now we'll have a power of g squared from this propagator, and then we'll have two powers here of, so here we have 1 over g squared, 1 over g squared, and g squared. So we are getting, let's see. Okay, and then we have, in addition, power of n from here, so we get this additional power of n. Now this should go like g squared n compared to this one, and I'm making some mistake, so your job will be to tell me where the mistake is. What? So there are 4 propagators, so this goes like cube, okay? It's this propagator, these 2 propagators, and these 2 vertices, okay? So this goes like g squared times g squared n. Okay. Now, as you start adding more and more lines, you find that, for example, let's add one more line here. Now we have, so when we added one more line, we added this, so here we had only one propagator, now we added this extra propagator here, and this, and another propagator here, and, well, this other third propagator, so we added 3 propagators, g naught cubed, and the 2 vertices, 1 over g naught to the 4th, and relative to the previous diagram, we added one more index loop, right? So this index loop runs from 1 to n, and so we have this factor of n, so this gets an extra power of g squared n. So this diagram goes like, now the one that is drawn there goes like g squared n squared. Okay, anyhow, so when you continue writing all these diagrams, you find that each diagram contributes with power of g naught to the number of propagators minus number of vertices and times n to the number of loops. Okay. You can, and this will be some diagram that, well, you'll have all these different lines that join together, and you have that feature. Now you can think of this diagram as some kind of geometric figure. So here you can think of it as living in the plane, for example, and as having some faces. Each face will be one of these index loops, and some vertices, which are the lines where the points meet, and some sides, which are the propagators themselves. And so you can rewrite this as, so the number of loops, you can rewrite it as the number of faces, and then you can multiply here by n squared and subtract here, well, this combination. So we said the number of propagators was the number of edges plus the number of vertices, and times g squared n to some power. Okay. So this is how the generic diagram would go like, and this combination is 2 minus 2h, where h is the genus of the two-dimensional surface that we built out of the diagram. Okay. Now let's see some examples. So, well, we already saw these examples here in the propagators. Now, so for example, if we had vacuum diagrams, this would be a diagram we can draw on a sphere. This is another diagram we can draw on a sphere. Now, a diagram we cannot draw on a sphere is something like this. Let's see. Okay, so this is a diagram we cannot draw on a sphere, so it's here going over, and here all the orientations of the lines should match together, otherwise I've drawn it incorrectly. So you start with this line, you go around here, so this comes back down here, then we go around here, go around, this has the opposite orientation, that's pretty good. We come down and we go back out. So we just traced only a single boundary. This diagram actually has a single boundary, so we have a factor of n, and it has, well, 1, 2, 3 propagators and 2 vertices, okay? So we'll go like chi square n. Now, these diagrams, well, let's start with this diagram. I forgot to say how they went like. So this, again, has 3 propagators, so the same number of propagators and vertices as this diagram, except that it has 1 more index loop, okay? So this goes like n. Okay, again, sorry, this has 2 more index loops. So it has this index loop in the interior, and then the index loop outside, okay? So the sphere diagrams go like n squared times a function of Gn. The torus diagrams go like just n squared times some function of n to the 0 times some function of Gn. So the sphere has h equal to 0, genus 0, and this torus has genus 1. This agrees with this more general formula here. So as an exercise, you can draw this diagram on a torus and see that you can draw this diagram on the torus without the lines crossing. Okay. Okay. So then what we conclude is that the sum of all planar diagrams will give us a partition function that goes like n squared times some function of chi square n. So this is the sum of all planar diagrams. So this is the partition function of the full field theory to lead in order in n. So if we take a limit where so we can take the limit n going to infinity and chi square n fixed, okay? Let's say of order 1 or smaller than 1 for the moment. So then, in this limit, this is the dominant contribution to the partition function. All the other contributions go like n to the 0 and some lower powers. So this is the limit that I'm interested in taking, the Toth limit. And so what we see is that in this limit, the different Feynman diagrams divide themselves according to the topology of the surface where we can draw them, when we draw them in this double line notation. Okay? Okay. Now, this sum over diagram, this sum over different topologies is a little suggestive of a string theory, where again we sum over different topologies of the worldsheet, where we start with a spherical worldsheet, we go on to a toroidal worldsheet, and so on. So this looks a little bit like a string theory, and that was pointed out by Toft in the 70s. And now, what is this string theory? So the idea is that if G square n is very small, then there are a few diagrams that contribute that are very important, that say here we were computing the free energy, the dominant contribution would be something like this, and then this would be a subleading contribution, and so on. However, as Gn gets increased a bit, so when Gn starts getting larger, there are more and more terms in this series that contribute. Okay? So the idea is that when Gn gets large enough, there will be a large number of diagrams that contribute, and this, a typical Feynman diagram that contributes will look like some surface with lots and lots of little holes, which are these index loops, and then joined by propagators in many different ways. And so the idea is that two-dimensional, there will be a two-dimensional surface on which some fields live, and maybe you can reproduce the results of these Feynman diagrams by thinking about a two-dimensional about the field theory on this two-dimensional surface, and the discretization of that theory will be the Feynman diagram. And when you get lots and lots of index groups, you get some kind of continuous two-dimensional worldsheet theory. Now, this is not telling you what that continuum worldsheet theory is. So in the limit of very large, when the top coupling gets large enough, maybe the theory simplifies in the sense that the continuum worldsheet theory will be some simple theory. Maybe, or maybe not. So it depends on the case. Okay, so this argument is not telling us what the worldsheet theory is. For that, we'll need to make some guess. So the idea is to derive from here that it should be some kind of string theory, and now make some guess on what this string theory should be. Now, first of all, we need to make one remark, which is that, well, here in this argument, we treated chi square as just some parameter of the theory, but in a theory like QCD, for example, chi square runs. It depends on the energy. And so what are we saying here? Well, one observation is that if you rewrite the beta, so you can call this lambda, and this parameter lambda, but this will not be a parameter, it will be something that will depend on the energy. So if we do experiments at different, lambda will have different values, and so then the string description will be most, let's say the string worldsheets will be very big and so on, in the limit that lambda gets large, okay, or gets close to 1, or gets to a region where the series doesn't converge. The series of that defines this function. Okay, so that's one point. Now, the second point is that this parameter has sort of a smooth running in the Larsen limit. But what I mean by that is that when you rewrite the beta function in terms of lambda, you find that the beta function it can be rewritten as a function just purely of lambda and not on n, plus order 1 over n corrections. Okay? Actually, let's order 1 over n corrections in SUN gauge theory. Okay, so in this limit, we'll find some lambda of E, and then we'll get that this top parameter will depend on the energy, but we still get something. Well, we expect something. We expect a simplification in the limit. So we'll only have to sum of these planar diagrams. What the sum is, well, depends on the energy of the process we consider, and that's it. Okay, so now, yeah. Well, here the only precise dimension is the dimension on which the field theory lives. So the field theory lives in, we said 0, 1, 2, 3, etc., some number of dimensions. Well, we'll get into that in a second. Okay. Okay. Now, one little remark is, well, you can, as an exercise, well, maybe I should just mention, if you have extra fields that are in the sort of fundamental of UN, so this Lagrangian has a UN symmetry under which M goes to UM, U minus 1, and you can add extra fields that transform in the fundamental representation of UN, and those in this worldsheet description correspond to adding here extra lines that are single lines, not double lines, and those are should be thought of as boundaries on the worldsheet. So we have these quark lines that maybe we denote with a and gives us the interaction between the linear interaction between two gluons for weak coupling. But then we have all the other diagrams, and all these diagrams here build the two-dimensional surface. And the idea is that this string is the same string that will, for example, give us confinement in usual bosonic Yang-Mills theory. Okay. So this is a string that goes between a quark and an anti-quark, and so on. Now, a quark and an anti-quark If they are dynamical, so they theory. So the mesons are open strings. And if we don't have any open strings, then we have pure strings would be glue balls of the Young-Mills theory. So objects made only out of the Young-Mills fields. Now, well, this string picture, so in the interaction among strings, so the string interaction parameter is the loop counting parameter. So here, when we go from the sphere to the torus, we lose 2 powers of n, and in standard string theory, this ratio is the string coupling squared. Okay. So what we find is that the closed string interaction coupling constant, this is the string interaction that we confuse with the Young-Mills coupling, is 1/n. Okay. So for very large n, these open strings will also be weakly interacting. So the open string coupling is sort of the square root of the closed string coupling, but in any case they will be weakly interacting. And so the fact that mesons in nature are also weakly interacting can be thought that maybe n equal to 3 is good enough approximation for large n. So there is the hope that maybe n equal to 3 is close to n equal to infinity. Okay. And so the idea is that you would solve the theory for n equal to infinity and then do an expansion in terms of 1/n and then set n equal to 3. Okay. And there are some features of QCD which seem to qualitatively agree with the large n picture, like the fact that mesons interact weakly, that mesons seem mainly constituted out of a quark and anti-quark and not 5 quarks, for example. Not 4 quarks, for example. I mean, for two quarks and 2 anti-quarks, for example, they are not. Maybe I should say this more properly. So a meson is mainly seen to be something like this and not something like this, for example. These normally are like 2 decoupled mesons. There is another feature of the presence of strings, which is ratio trajectory, which is if you look at particles with, let's see, as a function of spin, you look at particles which have the minimum mass for a given spin, and you find that they lie on straight. And so the of this type, which have if you have a rotating string. So as an exercise, take a straight rotate with constant angular velocity and find that the string obeys this relationship where alpha prime is the inverse string coupling constant. Okay. Now what we'll find is that well, and finally confinement is also thought to be associated to a string. So the string is the flux color electric and magnetic flux tube going between a quark and an anti-quark. But we'll later see examples where that have a dual description in terms of strings, but they are not confining. So confinement is not the real thing that tells us that we have strings. Though confinement is very naturally explained if we have strings with finite tension in the 4-dimensional theory. Now, okay, so here we discussed these Feynman diagrams. Now we'll discuss some correlators of operators. So if we, again, in the spirit of doing the counting for large n, so we consider operators of the form n trace of some function of m, okay? Now so this operator corresponds, we can do again an expansion of this operator in terms of powers of m, and the operator is, let's say, the cubic term in m. The cubic term is like the insertion of some object like this, where I mark it with a dot by meaning that this is not the vertex that was initially in the theory, but this is the insertion of this special operator. Okay, so the operator is some combination of vertices of this type with some particular coefficients which are just determined by this function. Now, with this normalization is in the large n limit. In the top limit is the same basically as the normalization we had originally in the action. So adding this operator is like adding an extra term to the action with some small coefficients. And so what we'll find is that if we have, for example, the insertion of two such operators, where we can draw, well, we basically have a two-dimensional surface with a marked point, which is this special vertex, and then we have all the other vertices of the theory. Okay, that's the leading contribution to the correlation function of just the expectation value of this operator. Okay, it will be this, and then the torus with a marked point, and so on. Okay, this looks very similar to what we to the correlation function in string theory, where we take in the correlation function of a vertex operator, so the vertex operator on the string worldsheet, and then we integrate over the string worldsheet. And then we sum all topologies. Now, when we have two such operators, so suppose we have O1, O2, then the leading contribution will be two spheres with one each a mark point, so mark point number 1 and mark point number 2, which are the insertion of these two operators. So that's the leading contribution. And so we see that, and then there are some other contributions, sphere with the 2 points on the same sphere. Okay, but this contains two spheres, so this has a larger power of 1 over n squared. Sorry, larger power of n squared. So and equal to the square of this, so, well, not the square, but the product of these two, plus corrections. So in the large n limit, correlation functions of single operators factorize. Okay, so this is the factorization of amplitudes at large n. So it's an important property of theories at large n. So this factorization is normally interpreted as saying that there is something that is behaving classically in the theory. So this, because in a classical theory, so when we compute the values of some operators, of products of operators, of course they commute, and they're equal to just the values we consider when we consider only just one operator. Okay, so this obtains some classical values, and these are the leading terms we get in the large n approximation. So, well, well, there are a couple of other properties we can point out. Is that so this contribution is a disconnected contribution to the correlation function. So there are two disconnected. These Feynman diagrams are disconnected. That's the leading contribution, but one might, in some cases, be interested in the connected contribution between O1 and O2. See that the leading contribution will go like a sphere diagram, so it goes like n squared. And in fact, all correlation functions, the connected part, all correlation functions of any number of operators goes like n squared. Okay. That means that, I mean, if we compute relative ratios like the 3 operators divided by O to the 3 halves, this goes like 1 over n. Okay. We'll later compare this with formulas we get from gravity. Okay, so finally, let us mention one simple operator that we are going to be interested in gauge theories, which is the Wilson loop operator. So this is an operator that is constructed by taking an arbitrary contour in, let's say, 4 dimensions, and then integrating the gauge field along this contour, performing the path integral. So this is a path ordered exponential of the connection around this contour. Then we take the trace, and so this is the Wilson loop operator. Now, what's interesting about this operator is that in a confining theory, the expectation value of this operator should go like e to the minus area of the surface enclosed by this contour. Okay. I guess, are you all familiar with this? Yes? No? Yeah, it's important the operator is normalized like this for this argument. Yeah, that's right. If you have the identity, it will be like n squared. Okay? So in a way, this is the simple normalization. So this is the normalization. So the way to remember what this normalization was is that it's the same as the normalization we have in the action. So in the action, we have that 1 over c squared, but in the soft limit, we can rewrite this as n over c squared n. So this has some constant, okay? So again, we have this overall factor of n, and then adding this operator is like changing a little bit the action, like introducing an extra vertex. So this is this extra mark point here that we were talking about. And this is a simple normalization because this is precisely what we do when we do string theory. This is how we normalize vertex operators in string theory. Well, if we are computing scattering amplitudes, we normalize them a bit differently. But this is how we normalize them if we are, for example, considering the sigma model action, dx squared, plus, let's say, some small perturbation, delta h dx, where delta h is a graviton perturbation. Okay? So this delta h here with no factors of g in front, this is this normalization we are talking about here. I don't know if this is clear. Yeah. Okay, so I mean, this is the normalization that natural in the classical, in the large n limit when we view it as a classical limit. So we have the action that goes like this overall factor of n, and then we have these functions, and these functions are the ones that remain constant. Okay, so okay, as we said, we don't know what the string theory is, so so all this discussion will well, it's useful that we counted the powers of n and so on, but in terms of string theory, it's not very useful yet because we haven't said what the string theory is. So we need some way of guessing what the string theory is. So the most naive guess is to say, well, if we are in d equal to 4 and we have a 4-dimensional Yang-Mills theory, for example, then the string should live in 4 dimensions and should have the simplest action that, so we try some action in 4 dimensions, so the simplest action is just the Nambu action, so tension times the area. Okay, so it's just the usual Nambu action that you already seen many times. So let me write it a little more explicitly. So we can write it in Polyakov form. Okay, so this is the action, and then we just quantize this theory, and that should be some approximation to 4D Yang-Mills. And this is actually how, well, I mean, this action was one of the first proposals for describing strong interactions. So along with Veneziano and so on, it was the origin of string theory, trying to describe strong interactions through this simple action. But this doesn't work. And the reason it doesn't work is that this action has the Weil symmetry. I suppose you talked about this, under which the worldsheet metric changes to omega g. And this is a symmetry of this classical action, but it's not a symmetry quantum mechanically unless d is equal to 26, okay, of an action of this type. So this didn't work because we wanted to solve Yang-Mills theory in 4 dimensions, not in 26 dimensions. Okay. Now you can one thing you can do is you can actually compute what is the change. So when you compute, so a string path integral is an integral dx and an integral dg of e to the minus s of x in g, and you can compute the change in the effective action. So this will define effect. And so we pick some we fix reparametrization invariance, and by picking some metric g equal to e to the omega times g hat. And now we do this integral, and here we'll have to integrate over the ghosts that are responsible for this fixing, and C and D and so on. I think you saw this already, right? Yeah. Okay, so this will give you some action that will depend on this on phi. Let me call this phi, on this field phi. It shouldn't have depended. I mean, classically it would not depend on phi, but quantum mechanically it does. And the dependence is so you find the following dependence, that so S at the metric G, which is e to the phi times g hat minus S in the metric g hat, is equal to 26 minus D times the integral Okay, so you find that this is the dependence on phi, and so now something you could do is, well, I mean, things should have been independent of phi, but what we can do is we can just integrate over phi, so we can quantize this action. Okay, and indeed this action can be quantized if nicely if D is 0 or D is equal to 1, and quantizing this action gives the right values for these two values. Now I won't go into the details of, well, of exactly what goes wrong if D is bigger than 1, but this is the right answer if D is less than 1. So in summary, the right answer for D less than 1 is that you start with the naive string theory, let's say in 0 or 1 dimensions, and add one more dimension. Okay, so we started with the dimension x. Let's say we are in equal to 1. We started with the dimension x, and now we add this dimension phi. So the string that ordinarily we thought was living in only 1 dimension, because we had, let's say, quantum mechanics theory in this case, now the string should live actually in 2 dimensions. So the main lesson we get from here is that the number of dimensions where the string theory lives need not be the same as the number of dimensions where the field theory lives. Okay? Now, I mean, in general, this procedure of, if you have some action that has some anomaly, and you calculate the variation of the action with respect to the gauge, well, to the symmetry that is anomalous, and then you try to integrate over that parameter, so this generally doesn't work. So if you had an anomalous gauge theory in 4 dimensions, this doesn't work, because the variation of the action is some nonlinear function of this parameter, and then you can't quantize it very easily. Well, you just really can't quantize it. But in this particular case, it does work in some cases. Okay, there's no guarantee that this method should work. It does work for D less than 1. Now, for D bigger than 1, we need something more interesting, something we really need to get some other string theory that automatically has no anomaly, that is automatically conformal invariance. Okay. Now, okay. Okay, so nobody so far has guessed the correct string theory for that corresponds to bosonic Yang-Mills theory, so to ordinary Yang-Mills theory with no supersymmetry in 4 dimensions. Okay, however, let's suppose that this argument about large n and so on is not restricted to particular theory, but is valid for any theory which, for example, has fields in the adjoint representation, so fields that are n by n matrices. And so in particular, we can construct a theory, and we'll later see one example, that is actually scale invariant in 4 dimensions. So it sounds that, so if you had a theory that is scale invariant in 4 dimensions, okay? So we'll consider scale invariant gauge theory in 4 dimensions and consider the large n limit. And so this is supposed to give us some string. And we already saw the string will have to move in at least 1 more dimension, so at least 5 dimensions. But the string should have all the properties, all the symmetries of the theory. So let's try to guess what the 5-dimensional spacetime. So in order to say what the string theory is, you have to say in what spacetime this string theory propagates. Okay? How does this new dimension combine with the previous dimensions? Okay? So we'll have to give some 5-dimensional geometry. So what could this 5-dimensional geometry be? Well, this 5-dimensional geometry has to have all the symmetries of the field theory. So that is, if the field theory lives on R4, so we'll have to have all the Poincare symmetries of 3 + 1 dimensions. And then a generic metric can be written in this form. So some arbitrary function of the extra 5th dimension plus these 4 dimensions. Okay? So that's some 5-dimensional space-time where the strings will be propagated. Now, in addition, this theory should be scale invariant. So the field theory was scale invariant. Now, this scaling symmetry cannot be just an ordinary, well, suppose we had 5 flat dimensions, then we could imagine that the scaling symmetry in 4 dimensions corresponds to just scaling all the coordinates in 5 dimensions. But string theory is not scale invariant because there is 1 dimension, so there is 1 scale which is the string tension. Okay? So string theory is not a scale invariant theory in d dimensions. So in order to make it scale invariant, it should happen that the scaling of these coordinates should combine in such a way that it becomes an isometry of this space. So it should leave this space invariant. Okay, so what is that scaling symmetry? So it's sending x to lambda x, and so this will get multiplied by a factor of lambda squared. So we see that if we set c to lambda c, then this gets multiplied by the same factor. And then we see that if we pick w of c, which goes like 1 over c, then this 1 over c here will cancel the factors of lambda we got from the other terms. So in the end, if we pick such a metric, this metric is invariant under those transformations, these kinds of transformations. So these are like scale transformations in this 4-dimensional space, but as a 5-dimensional isometry is just an ordinary isometry. It leaves the metric invariant. Okay, so we see that if a scale invariant 4-dimensional gauge theory has a string dual, the string should be moving in this space. Now this space is a 5-dimensional space which has a name, it's a well-known space, and it's called anti-de Sitter space. So this is called okay. Now, how does it look like? Well, let's. So we have these slices which are 4-dimensional, and we have this direction c. C will go from 0 to infinity, and at each point in C we have one of these 4-dimensional slices. And as we move towards larger and larger values of C, this factor in front of the metric becomes smaller and smaller. Okay? Now this factor in front of the metric is called warp factor. So this is just a factor that multiplies the time direction. Is normally called redshift factor. Okay. A warp factor is something that multiplies a bunch of dimensions in a way that is Poincare invariant in these 3+1 dimensions. This is just the name. Okay. So this warp factor here diverges at 0 and becomes 0 at infinity. And so here at 0 we'll have we'll see more in detail later, that we should think of c equal to 0 as the boundary of the space. And an important parameter of this space is this r squared, which is the radius of curvature. So this is a space that has constant negative curvature. And it's the most symmetric space with constant negative curvature. Okay, it's similar to Minkowski space in the sense that Minkowski space is the most symmetric space with zero curvature, zero constant curvature. And the most symmetric space with positive constant curvature is the zeta space. Okay, so the zeta space is roughly the same thing, except that the zeta space is roughly the same, except that what I'm multiplying the overall metric, it looks like this in some coordinates. And okay, and this describes an expanding universe. So if we take t going to from minus infinity to 0, so at 0 is the maximal sort of expansion of the universe. Now you're probably used to now let me discuss anti-de Sitter a little more. So in order to understand a little better what the isometries of anti-de Sitter space, what those isometries are, it's convenient to think about anti-de Sitter space in the following way. So you start with a Lorentzian type space-time with 2 time directions and 4 space directions. Okay? And in such a space-time, well, it has its usual Minkowski metric with 2 time directions and 4 space directions. And in this space-time, you consider a surface, a hypersurface, which obeys this equation. Okay. So, and then you consider, so anti-de Sitter space is this surface embedded in this space with the metric, and the metric on this space is the induced metric. So the induced Minkowski metric on this space-time. Now, anti-de Sitter space is a space with only 1 time direction, so you shouldn't be confused by these 2 time directions. So one of these 2 time directions is orthogonal to this surface, so it doesn't play any role in the physics of AdS. This is just to make the isometries more clear. So this makes the isometries clearer because this, the metric and this condition are both invariant under SO 2,4. Okay, so the Lorentz group with 2 time directions. So, and that's the group of isometries of anti-de Sitter space. Now, in order to see that this space is actually the same as the one over there, you can pick, let's say, some combination of these 2 coordinates, let's say x minus 1 plus x4, and call this r over c. So this is the definition of c. And then say that x mu, so this big X mu is equal to r over c times, well, I have a conflict of notation. Let's say this is little x mu, And this little x mu is the coordinate that appears over there. Okay? So as an exercise, you can check that if you define variables this way, and you define, so by solving this equation, you can compute x minus 1 minus x4. So this you compute by plugging these answers in this equation and solving for x and mu, and then you insert this into the standard, well, the standard metric here, and you should obtain that metric that we wrote before. Okay, so that's one exercise. Okay, so now this this form is also useful for choosing other coordinates. So another set of coordinates in AdS is the following. So you call the sum of these two things, you call cosine hyperbolic with a minus sign, cosine hyperbolic of rho, and this sum you call, well, times r squared. Let's set r to 1 for these purposes. So this you call minus cosine hyperbolic of rho. That's going to be the definition of the rho coordinate. And this you call sine hyperbolic of rho. Okay. Notice that by this condition, we can always solve for rho here. Okay. So this will always be bigger than 1. So the sum of these two things. The sum of these two terms will be always bigger than 1 if the surface is obeying this condition. And then the angle between these two things you call tau. And then here this is a surface at constant value of r. That's given by an S3. Okay. So finally we can write the metric. So in these coordinates we have space parameterized by one coordinate would be tau, then rho, and then a point on S3. Okay. And the metric, so you can compute here the induced metric in these coordinates, and you'll get ds squared equal to minus cosine hyperbolic of rho d tau squared plus d rho squared plus sine hyperbolic of rho squared d omega 3 squared. So this is the metric on a unit 3 sphere. Okay, this is some other set of coordinates in AdS. These are called global coordinates. Now it turns out that the coordinates that these coordinates here don't cover sort of the whole AdS space. So here there is some horizon at c equal to infinity, and particles can go through this horizon in finite proper time. So if you send the particle in, it can they can go through this horizon in finite proper time. Now, in these coordinates, we don't have any horizon, and these coordinates cover the whole AdS space. I mean, the reason we have this horizon is simple to see from the point of view of the hyperboloid. We had defined these coordinates r over c, and we took here c from 0 to infinity. So this will only work when this is positive, but this can have either sign, and so some reason. Okay. Some space-time, it's useful to draw its Penrose diagram. So the Penrose diagram of a space-time consists in rewriting this metric as some overall factor times some metric here, which has sort of a finite domain. So coordinates never go to infinity in this metric, roughly speaking. So in this context, what we do is we take out this factor of cosine hyperbolic of rho, and then we get this minus dt squared plus d rho squared over cosine hyperbolic of rho plus tanh hyperbolic of rho squared d omega 3 squared. Now here we can define a new variable x. So this is let's say y, new variable y, dy squared. And you see that when y goes from 0 to infinity, when rho goes from 0 to infinity, y goes from 0 to some value. Okay, some value which is given by the integral of d rho over cosine rho. Okay. Okay, so this metric here is the metric. It's a metric on a cylinder. on a solid cylinder, and this circle here at the boundary is really an S3, and this section here has the topology of a ball in R4, and this is the time direction. Okay, so this is the Penrose diagram of anti-spacetime. Okay, now, well, as you know, in Penrose diagrams, the light rays have simple behavior. So light rays are sort of 45. So the light-like lines in this metric, in the original metric, are the same as sort of light-like lines in this metric here, because they only differ by this overall factor, and for null lines this doesn't matter. And so here, so this is a Lorentzian cylinder. So here, if you have a light ray, the light ray will just go to the boundary here and reach here the boundary. Now, if here we put some reflective boundary conditions, then the light ray will come back in, and the time it takes for going here to the boundary and back is finite. And as an exercise, you can compute it. Okay, it's more or less, it's very, by looking at this picture, you should be able to, and computing what y is and so on, you should be able to compute this time very easily. Okay. So it takes finite proper time for the light ray to reach the boundary and back. Now, one question you can ask is, well, I mean, if the light ray takes a finite amount of time, proper time, well, let's say, roughly speaking, proper time to get here, why can't we just continue this light ray on some other surface here and just continue this space-time? Okay? What happens is that if you take geodesics, so if you just take a geodesic will have the following behavior. So any massive geodesic, so this was the behavior of light geodesics. A massive geodesic can never get to the boundary. Okay. So the boundary really sort of repels this the massive geodesics. Or another way of saying this is that all massive particles are attracted, roughly speaking, to the center of AdS. Now, truly speaking, there is no center in AdS because by an SO 2,4 transformation, we can take this geodesic, take a transformation, and transform into a geodesic that is just sitting straight here at the center. So they all can be mapped to this geodesic. But again, another exercise is to find these geodesics and again find how much time it takes for a particle to come back to you. So if you are sitting in anti-zeta space and you throw something out, after some time that thing comes back to you. Okay. So for a given observer in anti-zeta space looks like a gravitational potential well. Anything that you throw out comes back to you. Okay, and it comes back to you in some finite time. Even light. So light, you shine light out, and light will come back to you. Okay. So this boundary is sort of the inverse of a black hole. So a black hole is something that you throw something to the black hole and it disappears. This boundary is sort of the opposite. You throw anything to the boundary and it comes back. Okay? Nothing crosses the boundary. Okay. Now one thing that still left over is to relate this picture of AdS we have here with this picture here in global coordinates. We said that this was a horizon and this picture only covered part of that space-time, and so you can ask, well, which part is it? Well, it turns out that the situation is the following. So you have this cylinder, and the surface of the cylinder is S3 cross R. Okay. Now, if you compute the Penrose diagram of R4, which is one of the elements we had in this picture here, this R4 surface here at the boundary, the Penrose diagram of R4 is something that you can embed on S3 cross R. And it's basically like Well, you're all used to the Penrose diagrams in 2 dimensions, probably. So, for example, the Penrose diagram of 2 space is something like this. And well, it's the same story in higher dimensions, except, and then this, in higher dimensions, this combines with this radial direction to basically form an S3. So a Penrose diagram in 4 dimensions, handkerchief that you wrap around this cylinder. So here you have again 1 point, and then each line point expands in the S3. This is a point on the S3. Comes a big sphere here. On the other side. So we are wrapping the handkerchief on the face of the cylinder, and it's joining on the back. Okay, the 2 extremes. Okay, so that's this surface here. This is this when t time and so on go to infinity. That's the surface here, and this surface here at t equal to infinity. So all this interior is the some region which is within this handkerchief. So you can draw a null surface that starts here on the back and this thing on the top. And so this is a null surface. And so this null surface, okay, it's also c equal to infinity in this picture. Okay, so those are the horizons we talked about before. So here we said the trajectory of any massive particle is to start at some point here and make these oscillations. So if we start with some massive particle which is not here on the boundary of the cylinder but a little bit in the interior, it will start oscillating and eventually it will. Okay, and that's the same. In this picture, we would draw this as something like this. Okay? So from the point of view of just time on the boundary, it takes an infinite amount of time for it to cross the horizon, but proper time takes finite. Anyway, so those are some geometrical features of AdS. And so now let me make a couple of comments on conformal field theories. So do you have some questions about AdS? Or I probably should have stopped for questions. Please feel free to interrupt me maybe more often. I probably didn't stop enough. Yeah. Why we ended up with anti-zeta space? Well, I motivated it through a very hand-waving argument. So the argument was the following: that the string theory that is dual to a conformal field theory in 4 dimensions lives in 5 dimensions. Let's say at least 5 dimensions. Can be more, and in some examples there will be more. But let's suppose it lives only in 5 dimensions. Then the scaling symmetry of the field theory should correspond to some isometry of this 5-dimensional space. Okay? And the only space that has this right isometry is this anti-zeta space. Let me say it a little more mathematically. Maybe it won't clarify, but at least I make a correct statement. So the conformal group in 4 dimensions is some group. Turns out that the group is SO2, 4. The only 5-dimensional space that has SO2, 4 isometries is anti-zeta space. So the extra symmetry you needed was the scaling symmetry that we discussed. Now there are other ways of seeing that anti-zeta space appears, and I'll probably discuss it later by looking at the near horizon geometry of some black brains and so on. So far I only motivated somewhat loosely. Yeah. Yes. Yes. So this is okay. Now, what does it mean to be non-globally hyperbolic? So you can pick some initial slice here in anti-zeta. Let's say some this slice, okay? And now you want to evolve the data to the future. So you want to find out what the fields are on this slice here. But then you run into the problem that you have this boundary, and so information sort of can flow here in through this boundary. So it's not enough to know the initial data here, but you need to know something more. And so something more you need to know are these boundary conditions. And actually, we'll see that these boundary conditions play a very important role. So when we are talking about AdS here, we are thinking about this metric, and then all the fields that are defined on this space will obey specific boundary conditions at infinity. Okay? So just to be more concrete, suppose you had a scalar field here living in the interior. So a simple boundary condition for the scalar field is saying that phi is equal to 0 when, let's say, rho goes to infinity. Okay? So that will be, for example, a boundary condition we will impose. We'll later analyze these boundary conditions with a little more sophistication, but okay. Is there any other question? Yep. Yeah. So far, I've discussed this metric as a classical metric. Yeah. So here we discussed this as a classical metric, and really, eventually I started out talking about string theory. So this will then become some kind of stringy geometry, okay? But still classical in the large n limit. So the quantum corrections will appear when we consider 1 over n corrections. Sort of the Planck scale here in this geometry is basically like n, okay? So n going to infinity is the Planck scale goes to infinity, so that it becomes classical, okay? So yeah. By describing it purely geometrically and not in terms of stringy geometry, we are cheating a little bit here, okay? And so we'll later see under which condition this cheat is legal. Under which conditions can we talk about this space purely geometrically, and we can neglect the stringy corrections, and when the stringy corrections are important, and so on. This will come a little later. So keep in mind that they are there. But sort of before we said that there was something classical about the large n limit, that sort of correlation functions and so on behaved as if there was some object that became classical. In this relationship, the object that becomes classical is this geometry. So the geometry is the classical thing. And then by evaluating things on this geometry, we'll be able to calculate those correlation functions we discussed before. Okay, the leading contribution. Okay, any questions? Okay, so now let's see. Let's mention a couple of things about conformal symmetry. Did you discuss conformal symmetry? What? In 2 dimensions. Okay. Well, then I will skip this a little bit. So, as you know, conformal transformations are transformations that under which the metrics. Okay, what are isometries? Isometries are changes of coordinates such that the metric remains invariant. So the new metric is equal to the old metric. Okay. Conformal transformations where the metric changes. Where the change in the metric is some lambda times the old metric. That is, it is a diagonal change in the metric. Okay. Now, conformal field theories. So scale invariance typically implies that the stress tensor is 0. So if the theory is classically scale invariant, it's a stress tensor is 0. And then, if this happens, then there is a bit larger group of conformal transformations. In 2 dimensions, this group is infinite. In 4 dimensions, this group is finite and equal to SO2, 4. Okay. Now, so we have a finite group of transformations, of coordinate transformations, which are conformal transformations. In addition, if we have a conformal field theory, we can put it on spaces which have different metrics. So if you have some metric g mu nu, you can change it by some metric, let's say omega squared times g mu nu. This is a Weyl symmetry of the metric. And so if the theory had zero, the trace of the stress tensor was zero, then it will also be invariant under Weyl transformations. Okay? So conformal field theories that we'll consider are more or less invariant under transformations. So I say more or less because they are not exactly invariant. There is some anomaly under Weyl transformations, but it's a computable anomaly. And it's not different than the anomaly you had in 2 dimensions. So 2-dimensional conformal field theories were not exactly invariant under Weyl transformations. So, for example, they changed with the Polyakov action. So that was this anomaly, and we have the same feature in 4 dimensions. Okay. But in a sense, up to this anomaly, a conformal field theory only depends on sort of the conformal structure of the metric, that is, on the metric up to these scale transformations. Okay? So up to this anomaly. So the effects of this anomaly are normally computable, so conceptually one should think of the field theory as depending only on this conformal factor of the metric. Now, okay. So the metric on the space where, well, maybe one more thing about conformal field theories. As you saw in 2 dimensions, conformal field theories, there is a mapping between the states on the cylinder and oscillators on the plane. You saw this? Okay, and you can think of this as well. You start with the theory on the cylinder, in this case, let's say S3 cross R, and let's say you go to Euclidean space, and then these 2 spaces only differ by a Weyl transformation in the metric, so the 2 field theories are basically the same. And then, if you have some states here propagating on the cylinder, they will deform, let's say, what the path integral is at a given point in time, and that's the same as saying at a given point in radius, they'll deform the result of the path integral, and that's the same as what certain local operators do. And so in the end, so that's the state operator mapping, and so for each state here of the theory on the cylinder, there is a corresponding operator in the conformal field theory. Okay? So for a simple state like the vacuum, so if you have the vacuum state here, so what is the corresponding operator? What? The identity, that's right. So that's the identity operator. Okay? And so on, so you have the. Now here, you have the energies of states here on the cylinder, and the energies of states here will be, so will be what here? So this will be the dimensions, conformal dimensions of the operators. Okay? So like in, when you quantize the string, you find all these energy levels for the string oscillators and so on, and those translated into conformal dimensions of the corresponding operators. Okay. So this is a relationship that one often uses. So one can either think of the states of, it's sometimes a little more convenient to label states on the cylinder in terms of the operators on the plane, and we'll use this interchangeable. And in the literature you will find it used interchangeably. Okay, so okay, so far we're discussing this more or less abstractly. So now we'll discuss a specific example of a relationship between a field theory and gravity theory. So the example will be, so you take UN gauge theory, 4 supersymmetries. So with n equal to 4. This n is the number of supersymmetries. Now supersymmetries, well, you heard a lot about supersymmetries, and you probably already, did you already discuss n equal to 4 YAMLs? Yeah. So, what? Yeah, you have seen it. So, so this is a theory. So supersymmetry implies, well, as any gauge theory will have a spin 1 vector boson. Okay. Now supersymmetry will relate these vector bosons to other particles. Okay. So the other particles will be fermions, and so there will be a bunch of fermions. There will actually be 4 fermions. And then, since we have lots of supersymmetries, by acting twice with different supersymmetries, we'll get a bunch of scalars, and we actually get 6 scalars. I runs from 1 to 6, and these fermions are some fermions that carry, let's say, when they are chiral, they carry a fundamental index under, well, they carry an index that goes from 1 to 4, and when they're anti-chiral, again, they carry another index that goes from 1 to 4. So, and the theory is invariant under SO6. So this is an SO6 which exchanges all these 6 particles. And under this SO6, these indices transform in the fundamental and the anti-fundamental spinor. So the chiral spinor representation of SO6, chiral and anti-chiral. So these are these indices I and I bar. Okay. Now SO6 is sometimes, well, it's the same as SU4. So we can say that this is a fundamental index of SU4 and this is an anti-fundamental index of SU4. So this SU4 symmetry is a symmetry of this theory. It's a symmetry that does not commute with supersymmetry because different particles in the supermultiplet transform differently under the supersymmetry. So supercharges are charged under this symmetry. So this is called an R symmetry. And well, I should also mention that it acts chirally on the fermions, because fermions with one chirality transform in one representation, and fermions of the opposite chirality transform in a different representation. Okay. Now, okay, so now let me just write down roughly what the Lagrangian is. Well, I guess you probably have seen the Lagrangian, I'm told. So you have the YAML's terms, the kinetic terms for the scalar fields and for the fermions. And then you have potential for the scalar fields. Which is the commutator of 2 phi squared. And then you have some Yukawa couplings for the fermions. So this is, roughly speaking, the form of the Lagrangian. All these, the relative coefficients between these various terms are all determined, and there is only one overall coefficient here, the YAML's coupling. So there is a single trace that is over the UN indices. Of course, all these particles are n by n matrices. They transform in the adjoint representation of UN. And, well, there is another parameter which is a theta angle. So there is one more parameter we can add, which is trace F wedge F. And so this theory, okay, so this theory has a bunch of symmetries. So as we said, is well, classically this theory is scale invariant. You see that these interactions preserve. So phi has dimension 1. This is a quartic interaction, and again, this chi has dimension 3/2. This again, there's no dimension full coupling in the theory. So classically scale invariant, and more interestingly, when you compute the beta function is 0 to all orders, and so the theory is also scale invariant quantum mechanically. Okay. So if you had just ordinary YAML theory, that is just this it will be scale invariant, but then quantum mechanically it will not be. Here you have also scale invariant quantum mechanically. Okay. And then this theory also has conjectured S-duality symmetries. So the theory with coupling, so let's say first theta equal to 0, so the theory at coupling constant G and 1 over G are supposed to be the same. So, and so on. Okay, maybe I should stop here. Should I stop here? Should I continue or?